Good evening. In this video we are going to talk about the graphene, a material that is going to be the material of the future. We are starting with an introduction, and then we are going to explain the different properties, applications and uses of the graphene. Graphene is a single layer of carbon atoms forming a regular hexagonal pattern, extracted from graphite, with astonishing properties and impressive potential. Graphene is basically a single atomic layer of graphite. This is also in our pencils, an abundant mineral that is made of very united carbon atoms organized into an hexagonal surface. What makes graphene so special that it has a very thin atomic thickness. These properties are what enable graphene to break so many records in terms of strength, electricity and heat conduction. Before monolayer graphene was isolated in 2004, it was theoretically believed that two-dimensional compounds could not exist because of thermal instability when they are separated. However, once graphene was isolated, it was clear that it was actually possible, and it took scientists some time to find out exactly how. The problem that prevented graphene form from initially being available from developmental research in commercial uses was that the creation of high-quality graphene was a very expensive and complex process. Also, it was previously impossible to grow graphene layers on a large scale using crystalline epitaxy or any other dark metallic substrate.
I'm Nicolás. Now I'm going to explain the properties of the graphene. I'm starting with the electronic properties. One of the most useful properties of graphene is that it is a semi-metal with very high electrical conductivity. This means that we will be able to use it for processors in mobile phones or computers. Another of graphene's standard properties is its inherent strength. It's 200 times harder than the steel and almost as hard as the diamond. It is often said that a single sheet of graphene, being only 1 atom thick, sufficient in size enough to cover a whole football field. What makes this particularly special is that graphene also contains elastic properties. It can be stretched until the 25% of its size and is able to retain its initial size after strain. Now I'm starting with optical properties. Graphene, despite being the thinnest material ever made, is still visible to the eye, due to its unique electronic properties. It absorbs the 2.3% of light that passes through it, which is enough that you can see it in air, if you could manage to hold it up. It can react chemically with other substances to form compounds. Graphene is a perfect thermal conductor. Its thermal conductivity was measured recently at room temperature, and it is much higher than the value observed in all the other carbon structures as carbon nanotubes. Graphite and diamond, similarly to all the other physical properties of this material, its two-dimensional structure made it particularly special. Graphite, the 3D version of graphene, shows a thermal conductivity about 5 times smaller. The study of thermal conductivity is graphene may have important implications in graphene-based electronic devices. As devices continue to shrink and circuit density increases, high thermal conductivity, which is essential for dissipating heat efficiently to keep electronics cool, plays an increasingly larger role in device reliability. Now I'm talking about other properties. It is also impermeable impermeable. It is one of the lightest materials thanks to its thickness. It is capable to produce electricity when it is exposed to the sun, and many more than that we haven't discovered it already. Now I'm starting to speak about applications and uses that we could use in the future for the graphene. Graphene will probably be the most used material in the future. We will be able to use it in different ways. If we use in the way of energy, we can speak about lithium-ion batteries that recharge faster. These batteries use graphene on the surface of the anode surface. Defects in the graphene sheet introduced using a heat treatment provide pathways for the lithium ions to attach to the anode substrate. Studies have shown that the time needed to recharge a battery using the graphene anode is much shorter than with conventional lithium-ion batteries, the actual batteries that we use. Ultracapacitors with better performance and batteries is another of the uses that we will use. Ultracapacitors keep electrons on graphene sheets, taking advantage of the large surface of graphene to provide. This increases the electricity power that can be stored in the capacitor. Researchers are projecting that these ultracapacitors will have as much electrical storage capacity as lithium-ion batteries, but will be able to be recharged in minutes instead of hours. It will also have a lower cost in fuel cells. Researchers at the Ulsan National Institute of Canada and Technology have demonstrated how it produces edge halogenated graphene nanofibers that have good catalytic properties. The researchers prepared the nanoparticles by ball milling graphene flakes in the presence of sorbate, bromine or iodine. They believe these halogenated nanoparticles could be used as a replacement for expensive platinum catalytic material in fuel cells. More efficient dye-sensitive solar cells. In the actuality, we have very bad solar cells, but with the graphene it could perform better. Researchers at Michigan Technological University have developed a honeycomb-like structure of graphene, in which the graphene sheets are held a part of lithium carbonate. They have used this 3D graphene to replace the platinum in a dye-sensitive solar cell and achieved 7.8% conversion of sunlight to electricity. Another application would be for the lower cost solar cells. Researchers have built a solar cell that uses graphene as an electrode while using background.
Hi, I'm Javier again. I'm speaking about the uses of graphene in electronics. Lower cost of display screens in mobile devices. Researchers have found that graphene can replace indium-based electrodes in organized lights emitting diodes, or OLED. These diodes are used in electronic device display screens which require low power consumption. The use of graphene instead of indium not only reduces the cost but eliminates the use of metal in the OLED, which may make the device easier to recycle. Transistors that operate at higher frequency, the ability to ball high frequency transistor with graphene is possible because of the higher speed at which electrons in graphene move, compared to electrons in silicon. Researchers are also developing lithography techniques that can be used to fabricate integrated circuits based on graphene sensors to diagnose diseases. These sensors are based upon graphene's large surface area and the fact that molecules that are sensitive to particular diseases can attach to the carbon atoms in graphene. For example, researchers have found that graphene strands of DNA and fluorescent molecules can be combined to diagnostic diseases. A sensor is formed by attaching fluorescent molecules to single DNA and then attaching the DNA to graphene. When an identical single-strand DNA combined with the strand of the graphene, a double-strand DNA is formed that flows off from the graphene, increasing the fluorescent level. This method results in a sensor that can detect the same DNA from a particular disease in a sample. Chemical sensor effective and detecting explosives. This sensor contains sheets of graphene in the form of foam which change resistance when low levels of vapor from chemicals such as ammonia is present. In miscellaneous applications, membranes for more efficient separation of gases. These membranes are made from sheets of graphene in which nanoscale pores have been created. Because graphene is only one atom thick, researchers believe that gas separation will require less energy than thicker membranes. Low-cost water desalination. Researchers have determined that graphene with ores the size of a nanometer or less can be used to remove ions from water. They believe this can be used to desalinate seawater at a lower cost than the reverse osmosis techniques currently in use. Liquid natural gas tanks. Researchers at Rice University have developed a composite material using plastic and graphene nanoribbons that block the passage of gas molecules. These materials may be used in applications ranging from soft drink bottles to liquid natural gas tanks. Components with higher strength to weight ratios. Researchers have found that adding graphene to epoxy composites may result in stronger and stiffer components than epoxy composites using a similar way of carbon nanotubes. Graphene appears to bond better to the polymers in the epoxy, allowing a more effective coupling of the graphene into the structure of the composites. This property could result in the manufacture of components with high strength or weight ratio for such uses as windmill blades or aircraft components.
Thanks.
Thanks for listening to us, and we expect